Hello, good afternoon, everyone. How are you guys doing today? Started a few minutes earlier, just wondering if you guys have any questions about the assignment. Assignment 2 is due tonight at midnight. And we have another assignment to discuss today, a new assignment. So do you guys have any questions about assignment 2? No.
Hi.
Hey.
I had a question. So, in the test main script, do you want us, which function do you want us to use for testing the fifth vector?
The worry for testing?
Yeah, because it just says create 5 vectors using the cases shown above and then additional vector. And I was just wondering which function you would like us to test.
I would like both of the functions. Well, actually, it's 3 functions.
Okay.
So in principle, this script, you're right. We need to have 5 vectors. And yes, it says in the second bullet, on the third bullet point, use these 5 vectors. Using this 5 vectors, test all the 3 functions and display the results in the screen. So you don't need to use let me think, don't remember exactly how many cases, but at least I would say 3 cases per function. In particular, the ones that you will be more interested in noticing is the ones that we show in the example, so that you know that more or less the implementation is correct. But then when you do the part 1C, when you do the second implementation for your post-mean function to compare with your previous result, right? Be sure that that function is also giving you the right results. So usually this is a little bit of testing in the sense of comparing to results that you know, in this case, the ones I'm giving you, but then testing with results coming from different implementations. Usually this goes by in the big picture of things is what we call independent evaluations of the functions by looking at different algorithms, different implementations of the same in mathematical definition, if you wish, right? Does it make sense?
Yeah, thank you so much.
No problem. All right. Any other questions about assignment 2? As I say, it's due tonight. I think you guys are doing very well. I haven't seen many questions, so. Okay. If you guys don't have any other questions, I will keep my chat open. Let's get started with the lecture today. It's going to be a lecture that tries to summarize and bring together a little bit of the concepts that we have been discussing so far, giving them a more formal context, if you wish, or not formal, but at least giving the context of why it's useful to do some of the things I asked you to do in the assignments. Let me just pull my chat so I can keep an eye on your questions. Feel free also to unmute yourself if you prefer when asking questions. That's fine with me. Okay. So this lecture is about programming best practices. So we're going to be talking about coding etiquette, if you prefer, a little bit of modularity. This concept we have discussed a couple of times already. Testing, which is part of what you guys kind of did in assignment 2, and defensive programming, which is something we haven't done yet, but we may play a little bit with this in the future. Either way, it's a really good thing to implement in your codes, especially when you're working in projects that you want to make open to the community. It's a very, very important technique or tool or something to care about if you want to do that. It protects your code from misuse. That's what it's trying to achieve. So what are coding best practices? What do we mean when we say, or when I say coding best practices? Well, it turns out this is a coding techniques or practices that have been discovered over decades now, which allow us to produce code which is easy to write, read, debug, test, modify, and share and use with others. Basically, there are a set of rules which affect how you design the code and how you implement the code. For instance, I could have tell you, okay, with the assignments, go and do this, create a function that does this and that. I could have tell you nothing about writing comments. I could have tell you nothing about documenting the functions. I could have tell you nothing about using variables. None of that. It's up to you how you will implement that. By putting this sort of guides or guidelines or requests on my side about how I want you to write the functions, I kind of pushing you towards this philosophy or this style, more than a philosophy, of using best practices in code development, because this code, we believe, is going to be better for you, better for the community, better for the final user who is going to be using your code. Broadly speaking, coding best practices can be summed up as this: write code which is modular, don't write code which has already been written, meaning reuse libraries that can do what you want to do, write code which is easy to read and understand, and that accompany or encompass the concepts of documentation and comments and having indentation in your code. That's something I have been also mentioning to some of you, for instance, in your submissions. We have discussed a number of these points in previous lectures, but today we will discuss all of them in detail and coming together. And I will give you an example of how a code may look not following these guidelines, and then how we can transform that code into a code that is more within the ideas, within the concepts of best practices or coding best practices. Okay, please, as usual, feel free to ask questions, make comments as you see fit. Okay. So modularity, we have been talking about modularity. You guys have implemented modular versions of your functions because we have divided the problem into particular or specific areas and then implemented a solution for those. So what do we mean with writing modular code? Well, it's a code which is separated into individual functions and procedures. Each of them performs a single and specific task, like the means that you guys are computing. It's separated into files. Remember what we talked last time, the driver script, main driver script, and the utility files. And if you notice, in both assignments, I kind of guide you as well to create two separate files in R. Everything could have been in the same file, right? But I asked you to specifically create what we call our libraries, our set of utility functions, and then another file which sources that file, brings all those functions and make them accessible for us to use, and then execute those functions from within there. It's written also to enforce boundaries between the sections of the code. Again, divisions of interest or division of tasks or specific targets that each function has in place. This is going to be even more clear, I hope, on assignment 3. So we'll see that more in concrete there as well. And again, these concepts, I hope that we will definitely will accompany us during the whole course, but I also hope that it will remain with you as a way of working, because it will pay on the long run. Include testing routines to test the functions against non-correct answers, just what we were discussing a minute ago, right? If you know answers, if you know what the function should be doing, what it should be reporting, what it should be calculating for a particular case, test your functions. That's the best way to achieve that. It protects you against many different things. We're going to talk a little bit more about in detail about this, but it's not only protecting you against having bugs, which is something possible. Everyone has bugs in their code. If someone tell you my code is 100% bug free, don't trust that code. It's probably not the case. But it also helps you to understand difference in different operating systems. It's not the same a code running on a Mac, on a Linux machine, on a Windows machine. There are differences coming sometimes from the operating systems. Languages like R try to mitigate that as much as possible, but it's not always possible. So it's always good to have testing case that you know what it should be doing, and then if someone wants to run your code in a different operating system, a different machine, in a different environment, then you know what, if something is failing, it could be due to something different in the architecture or the operating system. So that's something that is important to keep in mind. So why does modularity matter? I think I mentioned some of the things, but let's go quickly through these bullet points. Scientific software can be really complex and large and subtle. So having divided it in modular parts is something that makes it more accessible to debugging and understanding the different parts. Each section of the code uses the internal details of other sections. You must understand the entire code at once to understand what the code in particular section is doing. So again, it's a way to have this separation of concerns in the codes. This is true. You can actually prove this. The interactions in a code grow as the number of lines of the code square. So if you have a code with 100 lines, the number of interactions probably will be 10,000 or something like that. So bottom line here is, as your code grows, it's going to get more and more complicated. If you can divide your code in smaller pieces that can actually be used in other projects, then you can just understand the single piece, and understanding simple things is better for human beings. So for us in general, right? So that's the main goal. It also helps finding bugs, mistakes, because if you have a smaller piece of code, it's easier to debug, to look at what it should be doing and understand if it is doing correctly. And also it makes writing testing routines for your codes extremely difficult, right? If you have a very long code, then you don't know if it fails one of the tests, you don't even know where it's failing, right? So having a smallest pieces of code help to debug, to write testing routines and find errors in which particular part of the code is failing. I always like to think about writing code as playing with Legos, Lego pieces that you put together to build something more complex and outstanding. Well, that's kind of the thing, but you start with a small pieces, very simple units that give you some sort of functionality, very simple functionality, and by combining them, you create something more elaborate. Doesn't mean that these pieces, you can see this as a kind of fractal behavior. These small pieces can be seen as small contributions to something bigger. You can start to test from the very small to the medium to the very large part of the code, right? So again, what I have seen is mostly some sort of the concepts and philosophy behind or that they compose best coding practices. What I'm going to show you now is an example of a bad code. So we're going to go through the code. We're going to discuss what is wrong with this code, what do you see that you don't like, or that you think it can be improved. And then we're going to see how to transform, how to translate this code following the best coding practices that we just discussed into a more modular implementation of this code, okay? So let me tell you a little bit of this code. This code, in a nutshell, what it's trying to do is trying to compute the energy levels of a given compound. Doesn't really matter. It's just doing some mathematical calculations. So it's defining some parameters here, number of elements in a matrix, actually, then a matrix of, in this case, 100 by 100 elements that will represent the eigenstates of the system, Hamiltonian of the system, if you wish, and then creating a vector of zeros for storing some data, okay? Then it has a function called PWU. It's a very cryptic name, if you ask me. It's kind of on purpose, of course. And then this function defines another vector, and then it loops over some things. It has two loops, two for loops, as you can see. Very nasty to see, actually, because they are on the same line. You can have this. You can actually type this whole code as it is, and it will work, with the exception of this something here, which is a complicated calculation. It doesn't really matter, but you can write one, and it will do something. And then it does some calculation there. It has this funny operator, which I show you this only once, and I hope that you will never see it and use it again, because it's a very mean, evil operator. It's for assigning global variables, and we know by now global variables are evil. So just I show you this to, if you go into the internet and look for something and you see this, you run as fast and far away from this operator as you can, because it's really bad, okay? Then there is another function, En, for energy, which does another calculation. As you can see, it's very hard to even follow. I kind of did this on purpose. Don't have indentation, I'm kind of giving you away some of the questions or the things that are wrong with this code, but it does the calculation of the energy levels, and that's the function En. And then comes some code block, another for loop, where it does another calculation, initialize a vector with ones, that's another calculation, initialize another variable with 0 and does another calculation, and then finally calls the PW function here, and then it says, okay, the ground state energy of this compound, whatever it is, and then calls this function, which by the way doesn't have any arguments. So this is what we usually refer in the jargon as a monolithic implementation of a code, because it's monolithic in the sense of, there is no parts where are clearly broken, and it's not modular. So it's a very, very heavy and not flexible code to work with. That's why also we call it monolithic. So this code uses functions, as you can see, PW and EN. So my first question is, do you consider, and I told you, I kind of gave you away some of the answers to my question is, do you consider this to be a modular code? And what things do you think are wrong with this code? And I give you just a few seconds to think about it and write something in the chat if you wish. So you guys will be okay if I give you no descriptive, excellent, Shada. No descriptive variable names. That's absolutely right. The names of the variables are horrible. Perfect, Peter, perfect. That is a very subtle one, but it's very good. Loops instead of slicing. Maybe you guys are appreciating how easy and how powerful are techniques like slicing and vectorization from the last assignment, right? And you're absolutely right. There are a couple of places here where it could be using vectorized operations, and we're going to see how we translate that into vectorized operations in a minute. Anything else that you would like to see in a code like this? Something that I have been asking you guys to put in your assignments. No comments, exactly. No comments whatsoever. That's terrible, right? And believe me when I tell you, this is not the first time that you are going to see code without comments, and that's really, really bad, okay? No comments, no docstring comments for describing what the functions are doing. I kind of teach you here with a comment in the slide saying, okay, this code has functions. Are we going to consider this a modular implementation? And the answer is no, because this code, even when it has function, is not modular. And I tell you why. Imagine that someone gives you this script, right? And you want to use the PW function or the EM function. Now, how I can do that? I need to source this script. And as soon as I source this script, not only will load the definition of the functions, it will execute the whole script. So for this code to at least beginning to be modular, what I had to do is I had to extract the definition of the PW function and EM function and put in a separate file, which can be sourced without executing anything else, and then I can use the functions wherever I want. So definitely this code is not modular. It has a lot of the mistakes that you guys had mentioned in the chat, and probably a few more that we're going to describe in a second, okay? So this is a kind of list. Global variables are being, that's another one. You saw in the functions, there are no arguments into the functions whatsoever. However, it's accessing the M variable representing the matrix and the A variable representing this vector. So these are being accessed by the functions without being received by the function as arguments. So that, again, this breaks modularity because I had to name my variables in that way to be able to use these functions, which is horrible, right? So that's one of the things. Global variables are modified within a function using this horrible operator. So that shouldn't never be the case, ever. All the code is in one file, monolithic implementation, as we say. The code has been copied and pasted. I don't know if you noticed that, but there are a couple of places where we have the same for loop here and here. It's exactly the same code, exactly the same code. It has been copied and pasted several times, okay? Definitely something we have said is not good because it's going to cost us a lot of trouble if we find that, instead of this multiplication factor here was a division, and then we have the bug spill all over our code if we have copy and paste. doesn't use existing R functionality. We're going to see some of the examples. Some of these functions we're trying to compute something that we can just compute with R. No use vectorization, as some of you was mentioning. No comments, no function documentation neither. No indentation of the code block. I don't know if you notice how hard it is to find, other than by the curly braces, how fine is to find what is the for loop being applied to. So again, that's something that can be so easily fixed by following, some etiquette in the way that we write our code. And again, that's something that you mentioned as well, very quickly, variable and function names, right? So let's see and try to figure out how to fix, how to actually write code that is appealing to be used and to be understood. So a word about global variable first. We have discussed this before, but don't use global variables inside functions without passing them into the function explicitly. This is sometimes a source of confusion. It's not that we cannot define global variables at the level of our main program. We do need to. There's no way, actually. It will be hard coding. It will be something really bad. But what we cannot is use variables within the functions that we define without passing them into the functions as arguments to the functions. That's the tricky part, right? We can define as many variables we want at the level of the main driver script, but those variables has to be communicated through the command line, through the arguments of the functions into the functions, okay? So that's the key element here. Why this is important? Because as I was telling you just a second ago, this will destroy your modular implementation. If even I separate these functions into separate files, the PWU function and EM function into two different files or one different file, these functions don't receive any argument. So they are assuming that when you're going to use this function, when you're going to call this function, you had a variable defined M and A, and not only that those variables represent what you're expecting to represent. So that's not the proper way of implementing these functions. These functions should receive this information through arguments into the functions, okay? I mentioned this smaller dash operator. What allow you to do, and I show you an example here, is in this case, because A is a variable of the main driver script, not passed into the function, is modifying the variable within the function. So if you want to do that, if you want to affect the value of A within a function without passing the variable or returning something, that's how you will do it. Definitely worst idea ever. Worst idea ever, worst implementation ever. I'm not even exactly sure why the language have that. Well, I know it's just for offering the functionality, but never use it. It's very dangerous. I'm serious about that. It's very dangerous. Same comment as before applies. You are assuming that variable exists, but then if you work in a modular fashion, you will say, okay, this function, unless it's returning something, won't be changing that value. And you work under that assumption. And if within that function there is an implementation like this, your assumption is broken. And then finding why that variable is changing, where you never change it, it can be a nightmare. So it's a really bad implementation in terms of programming techniques. It can lead to very, very undesirable side effects. So try never to use it, okay? This can be done, and I will show you how to mitigate this by just using a simple return statement as we have done before. Okay. What else? Okay, so let's start by trying to mitigate some of the things. First thing I'm going to do with this code is I'm going to start adding command line arguments, arguments to the functions, okay? So we are going to take the PWU function, and we notice that the function is going to use A and M, okay? That was something the function was accessing before. So first thing that we're going to do is pass the arguments A and M into the function, okay? The other thing that we notice is you look at the original implementation is this is looping over N, which N is nothing else than the length of A. So I can make all the reference to N just inside the function by defining what N is. N is how many elements are in the vector A. Okay, and now I have the vector A within the function. So instead of referring to N at the level of the main driver, now I define that. Q here is an internal vector that the function used to compute something. And then we are going to return Q. Instead of using the global assignation operator, we are going to return the vector that we just compute. Okay. Similarly, with the en function, now the function will receive a and m. And again, which is used within the function, is going to be determined within from the length of the vector that is received as an argument. And then we haven't touched much more than that, but basically receive now arguments in the function. When we call these functions now, instead of just calling the function without arguments, we pass the name of the variables that we want to use as the vector and the matrix. Okay, so now we assign this and we can compute the energy without major troubles. Okay, so the functions no longer use global variables directly. They receive the variables as arguments into the functions. Okay, is that clear? Any questions about this? Okay, now we talk about this, a single file. Now that we have variables that are passed as arguments into the functions, we can break this into different files. So we can split up into multiple files containing functions on similar functionality. That's our utility files, and you can have as many as you want. The general model in best practices is to have one driver program, the one that basically executes everything. Basically, I like to say it's like the orchestra director that tells the instruments when to start playing and stopping and make pause and so on. And then invokes utility functions or utility files. You can write as many driver programs as you need to perform your different analysis. You can have as many utility files as you want. The utility functions being separated from the driver program can be tested, and that is part of what we come after, and debugged separately from any other code in the same fashion that you guys are going or have done in your in assignment 2. You can actually load those functions. They are not executing nothing, so they can just define the functions and be tested for the results. The source command is the one that allows this driver program to load, to bring aboard the definitions of the functions. So let's now look how we can split this bad code that we saw at the beginning, this monolithic code. So we're going to split, for the sake of this example, in 2 files. One is, I told you this was actually computing the energy levels of the hydrogen atom. So we'll divide this into hydrogen utilities file and hydrogen.r, that's the main driver script. First thing that we can start by doing is putting some comments just to identify these files, to know what they are doing. So this is our function as before, nothing has changed. Only thing is I now put these functions in a separate file and I keep the main driver script into one single file. Now, one thing to just is for me at least is super enlightening is now I can look at these 2 simple files. It's way shorter, almost half of the size as the original one. And look, okay, let's focus just on the one on the right. Let's look at the main driver script for a second. It's a very simple driver script. It's sourcing something. I know that by sourcing is loading some functions definition. It's defining some variables to work with. Then it's doing some computation here. I'm not going to go into the details of this right now. In these 4 loop statements, then it's doing some other computations and then printing the result. So it's very straight to follow. I don't have to be distracted with what PW and EN definitions are. But then I can open my utility files and see the proper definitions of the functions. Still, there is work to be done on this side, but you can see the separation of concerns right away and see, okay, this program is defining some functions, doing some calculations, printing the final result. Okay, usually main driver scripts, where they're well implemented, they are super lean. Few lines, you don't really know, it's a very top approach that you don't really know much about the details that what is going on there. You can see some function calls, so you can see your source of utility files, but no details whatsoever. So there's still work to be done on this side as well, okay? But immediately you can see single files which are simple in their implementation, less code by separating them. But not only that, now these functions, the hydrogen utility file, can be loaded by any other main driver script, and can reuse these functions in a very modular manner. Okay, so that's our version 3 of the bad code. Still bad code, but moving towards a good code. Okay. Okay, identical blocks of code. We saw this in some of the examples, but we also mentioned this. Please do not copy and paste code, because that leads to terrible mistakes, and not only terrible mistakes. When you have a bug, your bug is a spillover all your code, and you need to go and look for all the implementations, all the repetitions of these pieces of code. So when there are chunks of copy and paste, what you need is a function. It's a function that defines that part of the code and reuses multiple times. Same idea. This is, again, hammering on the concept of modularity. So, well, let's see what pieces of code were repeated here. I think I mentioned this, but if you look at the PWU function, actually can use, the EM function can use the PWU function. And you see that here, right? So for I in sequence alone, blah, 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 can actually be implemented as part of, this is the implementation already. This is the original one. So the PWU function, which has 2 for loops, notice this, and then return Q, is basically what our for loop here is doing here. It's exactly the same for loop. Okay, if you look at this, it's exactly what it's doing here with the vector Q. So we can actually, within the EM function, call the PWU function. So if we do that, this is the implementation that does that. Now the EM function also only defines Q as being the result of PWU of A and M. Okay, so no code repetition whatsoever there. Okay, so we even simplify further our EN, our energy implementation function. Okay, so we remove the code repetition because we noticed that this part of the code was being actually reused in this function. Okay, what else? Use existing functionality. There are a couple of things, and again, this is tricky to see when you are looking at someone else's implementation, but when you are starting your implementation from scratch, if you know of a function in R that does something that you want to achieve, don't even think twice. Go for it. In the assignments, I may give you some restrictions, say, okay, I want you to implement this like what we did in the third part of the assignment 2. Don't use slicing, don't use certain functions, because I want you to go through the process of learning that. But in real implementations, by all means, if you know of a library that is well tested, if you know of a function in R that gives you what you want to achieve, just use it, right? And this is the case. In this function, in the PWU function, let's go back to this. What do you think this nested for loop is doing? There are 2 for loops there. What this function is doing the matrix vector multiplication. I know it's in the next slide. Do you guys remember how to obtain the matrix vector multiplication in R? If I want to multiply M times A, M being a matrix and A being a vector. If you go back, I think it was the last lecture or lecture before, we had this funny percentage, something percentage operator. That is what gives you the matrix vector operation. And that's exactly what the PWU function is doing. All that trouble, look at this function. Getting the length, having an internal queue, all that just for doing a matrix vector multiplication. Okay, so this is a string case, because again, if you know what you are after, you just will implement that. But look at the level of modularity here. We are having a function that performs that for us. And that is the level of modularity we want to achieve in our implementations. That simplicity, that specific task of a function to achieve. Okay. So now our PWU function, bearing that in mind, has been reduced to this very single or simple return of the matrix vector multiplication, or of the matrix times the vector. Okay, so that was what the 2 for loops, one next to each other, were doing. And now our energy computation function is the call to the PWU function, and then the return of the sum of A times Q. A times Q are 2 vectors now, I can multiply them. This is exactly what this fourth statement is doing. If you notice and go back to this code I showed you at the beginning, you may notice the same technique I asked you guys to use for the part 1C of the assignment 2. Initialize a variable with zeros, right? Loop over, and then accumulate something on that variable. Okay, so that should ring a bell now that you guys have gone through the exercise yourself. That is what this code was doing. And you went through the exercise as well. You notice that by using operations like sum and the inner product of A times Q, you basically can do that on a line, in one single line, super fast, super efficient, super clean, and clear in the implementation side as well. So look at these two functions, super simple functions implemented by using functionalities that are already offered us. Okay. So basically, PW function calculates the matrix multiplication. EA function just returns the sum of the product of two vectors. Okay. There is one more simplification that we can use. This calculation here, again, these are within the technical details where we refer to MII. Those are the elements in the diagonal of the matrix M. Okay. And what you can see is there is another function, diag, that basically gives you that. So these elements here, what we're doing is obtaining the maximum of the diagonal. Okay, you know that the diagonal in the representation of the eigenstates represents in this case, the maximum eigenvalue of the system is the one that governs the behavior of the system. Well, that's exactly what it's doing here. So is getting the maximum of the elements in the diagonal, and then basically subtracting the element from all the elements in the diagonal. So that's the simplification by using the diag function that are offers for matrices. Okay. So this is version 5. We have gone a long way. What else are we missing still? Well, we have missing the indentation, the variable names, the function names that are sensible, the name of the files which contain the functions, also sensible, name of your script, sensible, comments on the codes, and document of the function. So let's see how we implement some of the things here. Look at this code now. So just to give you an idea, some of you were asking me, and I think I was very, what's the word? I wasn't too harsh on assignment 1. It's going to be a little bit harder on assignment 2. I think I got some questions about comments and documentation, and I try to answer as clear as possible. But this is an example of what we are after when documenting and commenting our codes. This is just the utility files. This is the Hydron utility files, a general description of what this file contains, function used to calculate the hydrogen atomic energy states, and then the two functions. And look at this. This can be considered a little bit excessive, it probably is, but this function, which is one line function of code, has 1, 2, 3, 4, 5, 6, 7, 6 lines of documentation and 2 lines of comments. Okay. That is the level of usually what you see in professional code. More comments and documentation than actual code. It's a threshold. In average, people will say 50-50. Some people may think it's a little bit too extreme, but this is a good example, for instance. This is the Hamiltonian applied function. This is our original PWU function. Even the name is more enlightening now. Calculates the Hamiltonian applied to the state vector. And now the parameter A, I know is the state vector. The parameter Ham is the Hamiltonian operator, and then returns a new vector state. Okay. And then basically this is computing the matrix product of the Hamiltonian and the state vector. That's all. It wasn't so hard to comment. It was so much enlightening for someone reading this function. It's miles away of difference between one and the other implementation. Similarly, from the EN function, that's our ground energy function. This is the vector and the Hamiltonian, calculates the hydrogen ground state energy. The parameters are the same as before, but in this case, it returns the total energy. The first thing that it does is applies the Hamiltonian using the HANApply function, and then it calculates the total energy and returns that. Okay, so you can see what are we trying to achieve with the comments and the documentation of the functions. Clarity, clarity, and clarity. Okay. Any questions about this? This is almost our final version. I think it's the final version of the functions. There is no much indentation other than after we define the functions, one level of indentation for the documentation and the comments and the lines within the code block of the function. And that's holds for both of them, basically. Okay. So this is our modular implementation following best practices of the utility files. Okay, let's see how our main driver script look like. And again, you may see even a lot of, so you in the main driver script, you won't see documentation, but you will see a lot of comments. Okay, so this is the hydrogen.r script. This script calculates the ground state atomic energy of the hydrogen. It starts by sourcing the hydrogen utilities file, which contains the definition of the functions that we're going to use. Define the size of our problem, then defines the Hamiltonian operator and an initial state vector. So now, even without knowing anything about the field, you can read this code and understand what it's doing. Then initialize the Hamiltonian, okay? And you can see the indentation here for the for loop. Then compute the values of the largest diagonal elements and remove it from the diagonals. And then call the Hamiltonian applies 10 times, okay, just to mimic the process of iterations. And then print out the answer. So you have a comment of what the script is doing and what functions are being called and why. Okay. So this is our final version of the script. Now it's a modular, best practices following implementation. Any questions, any comments about this? If you probably go back to the list of bullet points I told you about best practices, you should be able to check next to each of these bullet points without any major issues, okay? All right. So no comments, no questions about this? All good? Okay. So we are going to switch gears a little bit, not a lot, because we are still in the topic of best practices, but we're going to start talking about testing. And one of the interesting things here is that now you have a very modular implementation, a best coding following implementation. Now we need to write testing routines. Okay, and the purpose of testing routine is to test the codes against known situations. That's exactly what we did at the end of assignment 2. And I tell you, there are different reasons why you want to do this. First of all, you want to test that your implementation works as you expect for known cases, but also you want to test your code in situations, in environments that is not where you develop. I have developed different packages in R, and I usually use either Linux or Mac OS. And sometimes I have found myself that the packages I write, they just don't write in Windows. They don't work in Windows because some things in the operating systems are different. So by testing in a different operating system also allow us to understand, okay, how can we make our code more robust? So that is why it's so important to include testing routines. You will notice also when you are installing packages in R, R will run a test provided by the developer that actually checks that the implementations are correct, that the tests are passing, basically. Okay. There are two broad categories or two main categories of tests that you can run. One is called integrated testing. Basically, you test the whole program. Like in the example of the Hamiltonian calculation, you test that the final result is the one that you're expecting given the initial conditions of the system. And that is called integrated because it integrates the whole process of running the script, includes and implies running the functions, calling the functions, initializing the values, and so on. So the final result is the one that you will expect. That is called integrated testing. The one that is a little bit more powerful is what we call unit testing, because what we can do in addition to test the code as a whole is to test, the individual modules, the individual parts that we use in the code. In particular, the functions that we define in our utility files. And that is what we're going to be talking about in a second, okay? So two main ways of testing: integrated testing, which tests the whole code. You look at the input that enters in your code and look at the output and says, okay, is this what I was expecting? If it is, then the code passes, okay? These different colors and shapes represent the different parts, the different modules the code may be using. But bearing that picture in mind, now we can talk about unit testings, where we take each of the functions. This can be, for instance, the initialization of the Hamiltonian. It can be the computation of the state energy, the calculation of the next state, whatever is part of your functions, and separate them because they're in a modular manner implemented, and test them individually. That's another of the good features of modularity. If this was the monolithic code that we had at the beginning, I don't have a way to test the functions. The only way I had to test the functions is copy the function, paste in a different script, and test the function. At that point, I had so many copies of the function, I don't know even what I'm testing, right? And I may change one, forget to change the other one. It's a mess. So the modular implementation allows you to test the actual function that you run in your code by just sourcing the utility file and testing that. So that's the main idea of unit testing: test the pieces of the code individually. This means writing code that will test the piece of the code in question, another main driver script, but its all functionality is to test those things. That's exactly what you did for the last part of the assignment too. Without knowing it, you were developing a testing script for your functions, and because your functions were developed in a modular manner, you can just source them and test them. This allows you to very quickly find bugs or problems, because if you know that the module yellow here is having a problem, then you just go and work on that, and you know that the other modules pass the test without any problems, right? So it speed up considerably the amount of debugging and the time that you are spending looking for bugs. So what type of tests we can run? So we are writing our testing code. What kind of tests can we perform? Well, we can compare things to analytic solutions if you have. Solutions tend to be for simple situations. If you doesn't get this right, you probably had serious problems in the implementation. So if there is a case, like let's say we are computing the electromagnetic field of a charge, and we know that it should decay as 1/r squared, for putting an example, then you can test the values of a given distance and then see if they match it or not. Other type of tests that you can run are benchmarking tests. These are very interesting, very useful tests that you do by comparing your code to other codes which try to solve the same problem. These are quite interesting because sometimes they can even lead to publications between different groups of different labs just by benchmarking, by testing the different implementations. So it's interesting. It doesn't demonstrate, though, that your solution is exactly correct. It just shows that everyone is mistaken in the same way. That's the way it goes, but at least it gives confidence on the field. You know, like if your competing lab is having the same results as you have, okay, we are at least on the same boat, right? Not necessarily a good end, but on the same boat. What else? Testing against reality. Again, this depends on the field of work, but if you can contrast against experimental results, then that's something definitely you should be considering. Okay. What else? So let's take a look how we will implement this in our example, the example we were discussing today. Okay. So this is a testing script for our utilities file. Okay. So what we're going to do is as I told you, we're going to source our utility file. We are going to define the size of a Hamiltonian. And then this is my testing function. Look that I'm defining a testing function here. That can happen in your testing scripts. My function will receive the vector, the Hamiltonian, the condition, and then the name of the test. Okay, so these are parameters that will accompany the function and specify what type of test we are running. So this is the same as before. Because we receive the vector, we can obtain how many elements are in the vector. And what we're going to do is we are going to apply the Hamiltonian and ask if this is equal to the condition. And if this is equal to n, which is the size, then it means that the test passed. If not, it fails. Okay, so this is the function definition called my test. Okay, and this is the way that we are going to run our test. So first we're going to run what we call an identity test, where the Hamiltonian is just the identity matrix. So that's a way to define an identity matrix, a diagonal of size n, and then the vector A is just all ones. So when I do this and I apply the Hamiltonian, what I get is just a vector of ones, because it's the identity multiplied by a vector full of ones. And then what I want to compare is against the vector A, which is a vector of ones. So my condition here is that all these elements are equal. Now you may notice I'm summing here, and this is some feature that comes from the Boolean representation that R does. When it finds a true, it's considered a 1. When it finds a 0, it's considered, when it finds a false, it's considered a 0. So it means that this comparison will compare two vectors. If the vectors are identical element by element, it will give me ones in all the positions. And by summing them, it gives me the total number of elements equal to n. So it's a shortcut to say each of the elements is equal to the expected condition that the expected result I want to get. Okay. So if this is true, then the test pass. If it is not true, the test fail. Okay. The linear test is another representation of the Hamiltonian, where we basically put in each of the rows the number of the row. So for I equal 1 to n, in the row I, we put the value I. And then what we get is, because the vector A is still identity vector, then you just get the same vector. Okay. And finally, we can do something like a back diagonal test, where we basically initialize the Hamiltonian with zeros, and then put in the Hamiltonian in the diagonal of the Hamiltonian, in the sub-diagonal, I should say, put values of I, and then we basically get, you can show this, is different kind of matrix multiplications, where you get the values from n to 1 in a decreased order. That's why it's called back diagonal test. In any case, it runs 3 different tests based on matrix vector multiplications, and it checks again what you expect to get as a result. Okay, so if we run our script now, this is a way to run in our testing script using R script, but you could just be sourcing the test script in your R terminal. What it will write is pass identity test, pass linear test, pass back diagonal test. So 3 tests that the function passes. Okay, but again, this is possible because we implemented a modular implementation of the functions that allow us to test that function. Okay, similarly, one could do tests for the energy computation function. Okay, any questions about this? Does this make sense at least? I hope it does. Defensive programming, just a few slides about defensive programming. That's something that we are not necessarily going to use a lot in this course, because it shies a lot when you are using command line arguments. But basically, the idea is that you want to protect the code from the user, usually it can be ourselves, from using it mistakenly. And this doesn't need to be on purpose. That can be that I just forgot the order in which I'm expecting the arguments, or the type of argument that my function is receiving, and I just calling my function wrong. So this means checking that the function arguments, or in the case of a script, the command line arguments meet certain criteria. So how this is accomplished depends upon the context and the programming language, but there are some common situations. For instance, check to make sure that the numbers are not negative when they shouldn't be. That's something that we sort of implemented in some of the functions I asked you for assignment 2. Check to make sure that the arguments are of the correct type. That we haven't done yet, but we could perfectly require that the arguments passed to the post-min functions are of type numeric. Remember the isNumeric function? Well, we could force that it's of type numeric. If not, if I pass you hello world as a string, then the function will fail. One very strong mechanism for those of you who are familiar with Python is the try-catch mechanism. It's complicated to implement, but it's very powerful because it allows you to try something. If it fails, it allows you to have a backdoor to actually inform the user without crashing the code. So it's something that if you are going to do serious R programming, you may want to take a look into, okay? So let's take a look at how we can do defensive programming in the functions that we have. So for instance, in the Hamiltonian apply function, we have the vector and the matrix, and we know that they need to match. So the second dimension of the matrix has to match the length of the vector so that the matrix vector multiplication can be done properly. If they don't match, the matrix vector multiplication doesn't make any sense, okay? And that's exactly what we are doing here. If the dimensions don't match, then we use this function stop, which basically stops the program from running, okay, and throw this error message to the users. If the dimensions match, then if this statement is ignored, and then proceed with the calculation, okay? Similarly, we do a similar check for the ground energy function, where in this case, the first dimension has to match with the length, so we can perform the sum, and then that's what we do. If the dimensions don't match, we stop the execution, we let the user know the dimensions don't match, and if not, we proceed with the calculation. As simple as that. Now, you can imagine as more arguments your function has, more of these checks you will have to implement, and this part of the defense that you put around your function of don't be misused or don't break in the function when executed. Okay. Documentation of your code. We talk about this. You must document your code. It's not optional. It's a must. In particular, in the best practices, implies having sensible variables and functions and class and module names, comments in the code, doc strings for documenting your functions. R provides several packages. We mentioned this. eHelp or docstring can help you experimenting with this, and it's a good idea that you try them. And it's always good to document the code, okay? In particular, you can source your functions and then run help. If you're using the eHelp package, you run help on the function, and we'll actually show you how the function, how the help of the function, how to use the function if you documented the function, okay? So a quick summary of what we covered today. Some of the elements of professional software engineer, that's where this is coming from, is modularity, testing, defensive programming, documentation, and comments. There is a fifth element which we are not going to cover in this course, which is version control, but I will strongly encourage you to take a look into these. Things like GitHub helps a lot implementing codes in version control system. It's a really awesome tool to take and to have under your belt. So I think that's all what I had for you today in terms of the lectures. Any questions about this? Okay, while you guys think, if you don't have any questions, let me show you what is going to be our assignment number 3. Okay. That's assignment 2 still. Assignment 3. So for assignment 3, the idea here, and I hope that you guys enjoy this, is to be working with real data from COVID-19. This is data collected by, in particular, the city of Toronto. For accessing this data in real time, what we're going to use is a package called COVID-19 Analytics package. Within the package, there is this COVID-19 Toronto data function, which provide access to the data. So what you will need to do for starting is open R and then install the package COVID-19 Analytics, okay? After you install the package, you will load the package, library COVID-19 Analytics, and this is the way to actually read the data from the city of Toronto. So you do COVID-19 Toronto data, then you're specifying the origin. This comes from the Open Data Initiative, and then the data format, which is the original format in which the data is reporting, the city is reporting the data, okay? And then you will find in this variable, if you execute this line, you will find in this variable the data, right? If you want to know more about this package, there's a lot of other things. You can look into this link, or you can just ask me, okay? But that's the package that we're going to be using for reading the data, for acquiring the data on real time. Now this is updated, I think daily, so your numbers may change. So bear that in mind. So the first task, okay, will be to install the package, play a little bit with the package. Your second task will be to create a utility files. We're going to call this covidutilities.r, and it will contain the definitions of the functions that we are going to be using in part 3. Okay, so in part 3, we are going to create what we call our main driver script, which is COVID process Tor COVID.r is for processing the data from Toronto. This will be our main driver script, which means it will source the utility file. It will define a function which will basically receive an argument, and that argument will be the year and date, a month, sorry, of the month that we want to process. So what will happen is you will source your main driver script, and then you will call, in this case, I call the main function process store data, and this will be the year 2020 and the month, in this case, October. Okay, it has to be in this notation because the data is reported in that notation. So the first thing is the argument will receive, the function will receive an argument. It will say when it's going to be processing. Like for instance, in this case, cases from 2020, 10, the month 10, October. And then the other functions will calculate and print the total number of patients per source of infection. And you have an example here. So for instance, total number of cases or incident type within the specified time period, in this case 2020-10, is by close contact. So these are the infections that happen at the month of October. By close contact 565, household contact to almost 1200, and so on. Now, this requires that you explore a little bit the data that you read here. Okay, so you will need to do a little bit of manual investigation of the data. That's the first function. The second function, what it wants is to calculate and print the number of confirmed cases in the ratios of age of 40 to 49. Okay, and again, you will see, if you explore the data set that you look here, how that can be determined. Okay, the final function is to calculate and print the neighborhoods with the most fatalities and the number of fatalities in the given date. Okay, so just to sum up, you will have 4 functions in your utility file. One function which loads the data and slices the data for the corresponding month that we indicated, year and month. A function that calculates and print the total number of patients per source of infection. A function that calculates and print the number of confirmed cases in a given range of age. And a function and calculates and prints the neighborhoods with the most fatalities and the number of fatalities. So in this particular month, this was endorsed par with 25 fatalities. Okay, so you will have to submit your main driver script and your utility files for this assignment. Okay, there are a couple of technical things that you may need to explore, but again, my recommendation will be to start by installing the package, loading the package, loading the data, explore the data, feel free to look at the data, feel comfortable with the data, learn about what is there, and then you will be able, with the techniques that we describe, this is more about data frames and slicing. So with the techniques that we describe in data frames, you should be able to actually go and dive into the data and dig into the data. Okay, so that will be the assignment for this week. Is due on April 12th at midnight, as usual. All right. Any questions about this? Probably you guys want to take a look at it. We're going to have our office hours on Friday at 2 p.m. as usual. I think it's at 2 p.m., right? And again, if you have any questions, feel free to reach by email or in the forum. All right. I think it's going to be a fun assignment. It looks a little bit overwhelming at the beginning, but don't be scared. Just play a little bit with the data, remember the concepts and ideas that we discussed in the data frame lecture, and also the ones that we discussed today. Modularity is going to help you, and it's going to be also requested in these implementations as well. Okay, so documentation of functions, commenting, best practices, and so on. Don't worry too much, though, about defensive programming. I'm not going to be looking for defensive programming for this assignment, right? Okay. So if you guys don't have any further questions, then we are going to be stopping now. Okay, no problem. All right, guys, I will see you either next week on the lecture or on Friday for the office hours. All right? Have a good one, everyone.